At 2:17 in the morning, a cow walks into a milking robot on her own. No one directed her. No worker moved her down an alley toward a parlor entrance. No gate swung open on a scheduled rotation. The cow, one of approximately 26,000 at Riverview LLP's dairy operation near Morris, Minnesota, approached the robotic milking unit because her body told her it was time. Her udder pressure had built to the point that the biological signal overrode whatever else she was doing. And she walked through the entry gate, stood on the platform, and waited for the machine to do what it does every time an animal enters. The robot's laser-guided arm extended beneath her. It located each teat in sequence, cleaned them with a brief spray, and attached the milking cups with a precision that required no human hand and no human eye. The vacuum engaged. The milk flowed. The machine measured output in real time. They monitored conductivity, a proxy for mastitis-related udder inflammation, and tracked the milking duration against the cow's individual production baseline stored in the system's memory. The entire process took 6 minutes and 14 seconds. Then the gate opened on the exit side, and the cow walked out. At that same moment, 14 other cows were moving through robotic milking units across the facility, and in a separate barn, the large rotary parlor that handles the higher volume portion of the herd was cycling through its scheduled rotation, a platform of 80 cows turning continuously under the attention of a small overnight crew. Riverview LLP produces over 260,000 pounds of milk daily. That production flows from a system that combines automated robotics with scheduled parlor milking, precision-fed rations calibrated to the individual animal's output, and neck-mounted sensors that monitor every cow's activity, study rumination, and health status around the clock. Morris, Minnesota sits in Stevens County, in the western prairie of the state. Flat land, cold winters, the kind of agricultural territory where large-scale dairy operations found room to build and water to support them. Riverview grew into one of the largest dairy operations in Minnesota by layering technology onto scale, using data systems and automation to manage a herd that no amount of human labor could supervise individually at this size. The system it built is what precision dairy farming looks like when it operates at 26,000 cows. The neck-mounted sensor is the data collection foundation that everything else in Riverview's precision management model depends on. Each cow in the herd wears a collar-mounted device that monitors 3 primary behavioral indicators continuously: physical activity, measured in steps and movement; rumination time measured by acoustic sensors that detect the chewing pattern of cud; and lying time. These 3 parameters, tracked together and compared against the individual cow's established baseline, generate alerts when the pattern deviates in ways that correlate with health problems, reproductive events, or nutritional imbalances. A cow approaching heat, the fertile window in her reproductive cycle, increases her physical activity measurably. She walks more, stands more, mounts other cows, and shows restlessness that the step count sensor captures within hours of onset. In a 26,000 cow herd, detecting heat visually, an experienced herdsman watching for the behavioral signs of estrus, is effectively impossible. The sensor system detects it without anyone watching. Rumination time is the metabolic signal that indicates whether a cow's rumen is functioning as it should. A healthy, well-fed dairy cow in active milk production ruminates 7 to 9 hours per day. Lying quietly, regurgitating feed, and re-chewing it with the slow methodical lateral jaw movement that the collar's acoustic sensor recognizes. A cow, whose rumination time drops below 5 hours per day, is either sick, stressed, or eating a ration that isn't supporting healthy rumen function. A cow whose rumination collapses suddenly, dropping from 8 hours to 2 hours within 24 hours, likely has a fever or a developing infection. The management software aggregates sensor data from all 26,000 collars simultaneously. Uli applies thresholds and algorithm-based scoring and generates a daily alert list that the farm's health and reproduction teams work through each morning. The list ranks animals by urgency, notes which parameter triggered the alert, and provides the cow's production history and recent health events as context for the person evaluating the flag. The system does not replace the herdsman who ultimately examines the cow and makes the treatment decision. It tells that herdsman which cow to examine. Again, a herd where the alternative is either missing early-stage illness or employing a workforce large enough to observe every animal daily by eye. Precision feeding at Riverview operates on the same logic. Individual variation managed through data rather than through the labor-intensive observation that small-scale farming permits. A conventionally managed dairy herd of a few hundred cows might receive a single formulated ration delivered to all animals simultaneously. Yet the ration reflects the average nutritional need of the group: energy for milk production, protein for amino acid supply, fiber for rumen function, calcium and phosphorus for skeletal maintenance, and milk component synthesis. Individual cows within the group vary in their actual needs. A cow producing 100 pounds of milk per day needs substantially more energy and protein than one producing 65 pounds. But at small scale, the economic and logistical cost of individual feeding makes group feeding the practical choice. At 26,000 cows, the economic case for individual precision feeding changes. The production value of the difference between feeding a high-producing cow adequately versus inadequately is significant when multiplied across thousands of animals. Underfeeding a cow producing 100 pounds per day pulls her into negative energy balance. She mobilizes body reserves to maintain milk output, which shortens her productive life, impairs reproductive performance, and increases health risk. Overfeeding lower-producing cows wastes expensive feed ingredients without corresponding production return. Riverview's precision feeding system assigns each cow to a feeding group based on her current production level, stage of lactation, the body condition score, and health status. High-producing fresh cows, animals in the first 60 to 100 days after calving, when milk output peaks and nutritional demand is most intense, receive rations formulated specifically for their stage. Mid-lactation cows receive adjusted formulas. Dry cows preparing for their next calving cycle receive a close-up dry cow ration with elevated calcium management to prevent milk fever at calving. The GPS-guided feed delivery system that moves rations through the barn complex delivers the correct formula to each group's feeding area on schedule, with quantities calculated to maintain consistent bunk availability without the waste of oversupply. The system records each delivery, formula, quantity, time, and the farm's nutritionists review bunk management data to assess whether intake matches expected levels and whether formula adjustments are warranted. The robotic milking units and the rotary parlor serve different portions of the herd for reasons that reflect the behavioral and production characteristics of different animal groups. Robotic milking works best with cows in certain stages of lactation and certain behavioral profiles. A cow that visits the robot voluntarily and consistently, arriving at intervals that match her body's production cycle, degenerates more milk with less stress than one that must be pushed through a scheduled parlor rotation. Fresh cows in early lactation, whose production peaks are high and whose udder pressure builds quickly, often visit robots more than twice per day during peak output. 2.5 to 3.5 visits per day is common for high producers in robot barns, compared to the 2 to 3 milkings per day that scheduled parlor rotations typically achieve. The robot's individual milk measurement also enables a layer of production monitoring that group parlor milking cannot easily replicate. Every milking of every cow in the robot system generates a data record: time of visit, duration, milk volume, flow rate, conductivity by quarter, and any anomalies the machine detected during the process. This data accumulates into a production history that the management system analyzes continuously, flagging cows whose production has dropped from their recent average, whose conductivity has shifted in a pattern suggesting subclinical mastitis, or whose visit frequency has declined in ways suggesting pain or reluctance associated with udder problems. The rotary parlor handles the portion of the herd better suited to scheduled group milking, typically higher capacity, where the throughput advantage of the continuous rotation platform outweighs the individual monitoring advantage of the robot system. The parlor's 80-cow platform rotates at a speed calibrated to the average milking time of the animals it serves. Workers or automated arms attach milking units as each cow's position passes, and the cow rides the platform through her milking cycle before stepping off at the exit point. No managing both systems simultaneously within a single large operation requires coordinated scheduling, labor deployment, and data integration that treats the two milking modalities as complementary parts of a single production system rather than competing approaches. 260,000 pounds of milk per day. The volume requires a cold chain infrastructure to match. The milk leaving the robotic milking units and the rotary parlor moves immediately into refrigerated bulk tanks that drop the temperature from body temperature, approximately 101 degrees Fahrenheit, to 38 degrees Fahrenheit within 30 to 60 minutes of collection. The cold chain cannot be interrupted. Bacteria in raw milk double in population roughly every 20 minutes at temperatures above 50 degrees. At 38 degrees, bacterial growth effectively stops. The bulk tanks at Riverview hold the day's production until tanker pickup, typically scheduled at 24 to 48-hour intervals depending on production volume and tanker route logistics. The tankers that arrive at the farm are dedicated to dairy transport, insulated and refrigerated, cleaned and sanitized between loads. They carry milk from Riverview to processing facilities within the regional distribution system that handles Minnesota's substantial dairy output. The Minnesota ranks among the top dairy states in the country by production volume and the processing infrastructure to handle that volume: cheese plants, butter operations, fluid milk processors, whey and protein ingredient facilities, though concentrates in the region. Riverview's daily output of 260,000 pounds feeds into that processing system as one node among many, but its scale makes it a significant node, one whose reliability, milk quality, and production consistency matter to the processors that depend on it. Somatic cell count is the milk quality metric that defines the operational boundary between acceptable and rejected loads. Somatic cells primarily white blood cells mobilized in response to udder infection, appear in milk at elevated levels when mastitis is present. A bulk tank somatic cell, count above 750,000 cells per milliliter, triggers regulatory rejection in the United States. The processing industry's practical threshold is often lower. A large dairy with widespread subclinical mastitis can fail a bulk tank test on the combined output of many individual cows whose individual cell counts would not trigger concern. Riverview's sensor-based conductivity monitoring and its individual cow production data feed into mastitis detection precisely to prevent that bulk tank risk. A cow with elevated conductivity in 1/4 generates an alert before her clinical signs become visible, before she's had multiple milkings adding high cell count milk to the tank, and before the problem spreads to other animals through contaminated milking equipment. Early detection and segregation of high cell count cows protects the bulk tank, while allowing affected animals to receive treatment. The anaerobic digesters at Riverview convert the manure stream from 26,000 cows into 2 marketable products: electricity and fertilizer. The manure volume from a 26,000 cow dairy runs approximately 400,000 pounds per day in liquid form, a figure that reflects both the mass of biological waste and the water that moves through the collection and flushing systems. Managing that volume requires infrastructure that treats it as a resource rather than as waste requiring disposal. The digester vessels at Riverview are large, sealed tanks where anaerobic microbial communities break the organic material in the manure down through the same biological process that operates in the rumen of the cattle that produced it, but under controlled conditions that optimize methane production. The bacteria require stable temperature. Riverview's digesters maintain mesophilic conditions around 95 to 100 degrees Fahrenheit, consistent organic loading, and management of the chemical conditions that allow the microbial community to function without the pH disruptions that kill the methane-producing archaea responsible for biogas generation. The biogas produced, a mixture of approximately 60% methane and 35% carbon dioxide, moves from the digester through a cleaning system that removes hydrogen sulfide and water vapor, then fuels generators that produce electricity. That electricity powers the dairy's substantial electrical load: robotic milking systems, ventilation fans across barn complexes, refrigeration equipment for bulk tanks, the lighting and heating systems in calf and maternity facilities, pumping systems for the manure and water infrastructure. The heat generated by the engines running the generators does not go to waste. To waste heat. Recovery systems capture the engine heat and use it to maintain digester temperature. The same heat that the bacteria require is produced by the generators, the bacteria's methane fuels. The thermal loop reduces the external energy input the digester system requires and improves the net energy output of the overall biogas to electricity conversion. The digestate, the liquid and solid fraction remaining after the methane has been captured, retains the nutrient content of the original manure. Riverview's nutrient separation system divides the digestate into a fiber-rich solid fraction and a liquid fraction concentrated in nitrogen and other soluble nutrients. The solid fraction, low in pathogen load after the digester's temperature and retention time, functions as animal bedding, a significant cost item in large dairy operations, and as a marketable compost or soil amendment product. The liquid fraction applies to cropland as fertilizer, supplying nitrogen, phosphorus and potassium to the corn and alfalfa production that feeds back into the herd's ration. The closed loop is real. Feed enters the barn. Cows convert it to milk and manure. The manure fuels generators and enriches crops. The crops return as feed. The electricity runs the robots that milk the cows. Minnesota's climate tests any livestock operation with a severity that temperate zone agriculture doesn't experience. Stevens County winter temperatures regularly drop below -20 degrees Fahrenheit. Wind chill on the open western Minnesota prairie extends those effective temperatures further. A 26,000 cow dairy cannot move indoors during a January cold snap. The cows are already indoors. The infrastructure around them must function continuously. Barn ventilation systems that maintain air quality during summer heat events must shift to minimum ventilation in winter, moving enough air to control ammonia and moisture without dropping barn temperatures into ranges that affect cow comfort and feed intake. The transition happens automatically, managed by temperature sensors and fan controllers that adjust ventilation rates without human intervention. The challenge is maintaining the balance. Too little ventilation creates respiratory disease pressure from elevated ammonia. Too much ventilation in a Minnesota January creates cold stress that shifts the cow's energy use from milk production to body temperature maintenance. Calf housing represents the most temperature-sensitive segment of the operation. Newborn calves are born wet, with limited body fat reserves, in conditions that can drop to -30 degrees. The calf barns maintain temperatures well above ambient through insulation, supplemental heating, and deep bedding management. Individual calf hutches or group calf housing with heated sleeping areas allow calves to maintain body temperature during the critical first weeks before they develop the thermoregulatory capacity of older animals. The reproductive program that maintains the herd's population runs through the same cold months. Calving continues year-round at Riverview, because maintaining a consistent fresh cow supply, cows in early lactation, when milk output peaks, requires fresh calvings distributed across the calendar rather than clustered in seasonal blocks. The maternity barn handles calvings at any temperature, staffed by overnight personnel who monitor calving progress and intervene when deliveries require assistance. The workforce that operates Riverview's 26,000 cow facility works within a structure shaped by automation, but not replaced by it. The robotic milking units reduce the labor required for milking by eliminating the need for workers to physically attach and remove milking equipment from each cow at each milking. A single robot handles 50 to 70 cows per day, with minimal human intervention beyond maintenance, cleaning, and management of animals that don't use the system appropriately. At 26,000 cows, that labor reduction is significant in absolute terms. What automation doesn't replace is the judgment-based work that requires human assessment. The herdsman evaluating the alert list generated by the sensor system each morning and deciding which animals need immediate veterinary attention, which can be monitored through the next data cycle, and which alerts are artifacts of the system misreading normal variation. The nutritionist reviewing bunk management data and adjusting ration formulas. The reproduction technician performing pregnancy checks and planning the synchronization protocol schedule for cows due for breeding. The mechanic maintaining the robotic milking equipment, the digesters, the feed delivery systems, and the ventilation infrastructure across multiple barn complexes. The data layer that makes precision management possible also creates a new category of labor, People who interpret data, manage software systems, troubleshoot sensor malfunctions, and translate the outputs of automated monitoring into operational decisions. Riverview operates with a technical staff that would not have existed in a dairy operation of this size 20 years ago. People whose training blends animal science, data analysis, and mechanical aptitude in combinations that traditional dairy workforce development didn't prepare for. The system that Riverview represents, large-scale dairy integrated with robotic automation, sensor-based individual animal monitoring, precision nutrition, and biogas energy recovery, did not emerge fully formed. Each element developed separately in operations smaller than Riverview before the economic case for combining them at this scale became clear. Automatic milking systems first appeared commercially in Europe in the early 1990s, initially adopted by small to mid-size farms in the Netherlands, Denmark, and Germany, where labor costs and farm structure made the economics viable. The technology matured over 2 decades before large-scale North American operations began integrating it as one component of a multi-system dairy. At 26,000 cows, no single technology defines the operation. The robots handle a portion of the herd. The rotary handles another. The sensor system connects them both to the management database. The precision feeding system responds to what the sensor system reports. The combination is what makes the scale manageable. Each technology individually addresses a specific constraint: labor for milking, visibility into individual cow health, nutritional precision, energy cost. Together they allow a herd size that would have been operationally impossible under the management systems available 25 years ago, when a herd of 26,000 cows would have required either a proportionally enormous workforce or a tolerance for aggregate management that sacrificed individual animal performance. The Riverview's model has influenced how the dairy industry thinks about the relationship between scale and technology. Large operations that expanded rapidly in the 1990s and 2000s on the strength of economies of scale in milk production sometimes found that the management systems couldn't keep pace with the biology at those numbers. Precision technology, sensors, robots, data platforms, changed the calculus by providing management visibility that scales with herd size in ways that human observation cannot. At 2:17 in the morning, a cow walked into a milking robot on her own. She will do it again in roughly 8 hours when her biology tells her it's time. The robot will be waiting. The laser arm will find her teats in the dark. The data will record. Somewhere on a server connected to the farm's management system, her production trend from the last 14 days sits alongside her rumination hours from yesterday, her activity score from the past 72 hours, and her reproductive status. If anything in that data shifts outside her individual baseline before the next visit, an alert will appear on the morning list. 26,000 cows, 260,000 pounds of milk per day, and a system designed so that no single cow in that herd is invisible to the people responsible for her. The technology makes the scale possible. The scale justifies the technology. That relationship, running continuously in western Minnesota, defines what precision dairy farming looks like when it reaches its current outer limit. If this look inside one of the most technologically advanced large-scale dairy operations in the country gave you a different picture of where modern agriculture is heading, hit the like button and help the algorithm find more people interested in these systems. Subscribe if you want to keep following the intersection of technology, biology, and industrial-scale food production. Drop a comment and tell us where you're watching from. We read them, and the geographic range never stops being interesting.